Okay, everyone, we're going to go ahead and get started for our final two presentations of the day. Hey, Stephanie, can you close those doors? Can you close those doors, please? Hey, Jeff, do you mind getting those doors for me, please? All right. Our next speaker is Dr. Mina Sartipi. She is the executive director of the UTC, or University of Chattanooga, Research Institute, and founding director of the Center for Urban Informatics and Progress. At the University of Chattanooga, she is also a Query Professor in the Computer Science and Engineering Department and holds a joint appointment at the Oak Ridge National Laboratory. As UTC RI Director, her work focuses on advancing cross-disciplinary R&D and experimental learning, leveraging Chattanooga's citywide mobility test bed, the nation's first commercial quantum network. She has contributed to over $40 million in funded research for federal, state, and private sectors. Dr. Sartipi has delivered keynotes and briefings to national audiences, including the U.S. Congress and major smart city and transportation forums. She serves on boards of EPB, the Enterprise Center, Chattanooga Design Studio, Siskin Hospital, and Variable Incorporated. She earned her Bachelor of Science in Electrical Engineering from Charlotte University of Technology and her Master of Science PhD in Electrical Computer Engineering from the Georgia Institute of Technology. Please join me in welcoming Dr. Mina Sartipi.
Good afternoon, and I'm so sorry about the earlier mishap of the technology. Glad to be here, and thanks for having me to talk a little bit about the work that we're doing here in Chattanooga. I'm with the university, but I work very closely with the city of Chattanooga. So a lot of times when I use the word we include the city and some of our partners as well. So as Terence mentioned, I'm the director for Center for Urban Informatics and Progress. And this is a center that is a multidisciplinary center at UTC. The goal is to work on really data-driven solutions for smart city challenges. And currently, a lot of our focus are on transportation. I'm by training, I'm electrical engineering, I belong to computer science department, I'm working on the transportation. But that is really, while I come from different backgrounds and working in different fields, this is really when the transportation is going. It's not what it used to be, and that's what is so important to multidisciplinary. And I'm going to talk a little bit about some other soft science areas that we also work with. But one of the things about what we do at CITE, and while this is a research center at the university, but we are really doing a lot of, I'm going to be talking about a lot of live work that we're doing at the university with a lot of our partners. It's a very close collaboration between public, private, and academic world. I'll be talking a little bit about the city-scale urban test bed we have and some of the ITS work that we are doing that are really deployed in the city, and we're seeing the impact of it. I'll talk a little bit about that. And what we are doing is a lot of the work is not really research for the sake of research. The problem actually comes from the community with the goal of how can we really improve the quality of life. What are the challenges? As an example, when we started about over probably was 8-9 years ago, one of the challenges that was given to us was pedestrian safety. That was the very first project that we did with Chattanooga. So that's one of the goals, and we really are trying to work with that and really we are like we have the commitment to innovation, but like really doing your work that can be applied. But how did all that start? Coming again from non-transportation background. In 2017, we received a fund from National Science Foundation, and the project was related on how can connected autonomous vehicle be deployed in an urban environment and really be able to be safe in a harsh environment. Like as an example, when GPS is out, or when the car, how can we bring connectivity to gain to be able to see that? How can we still have a safe transportation? The vehicle can go from point A to point B. If there is something extraordinary had happened, that the data that we usually rely on is not there. So when this was funded, one of the criteria that they had for us was we had to do a live demo. And while a lot of algorithms are developed in the lab, we were testing it on our computers, we did not have a place to test. So we had the three poles that you see up there. That is the street next to the College of Engineering campus, and we did not have any infrastructure. So you see here two of the students holding a pole with a camera because we needed to be able to see. And one of the things, we're human, so you start moving around. So we need to make sure that we had a reference point so we know exactly where things were. So we're using QR codes. We had posters that were hanging around our necks. We take turns to collect data and work on that. And it worked. We did a live demo in Austin, Texas, as a part of the World Congress for Smart Cities. It worked. We showed the impact and everything. But that was also when we realized that where are the challenges that we have when we are working in the world of ITS? The number one is lack of data, lack of real world data. You know, there are a lot of test tracks or offsites that they can collect data. They are data, but what are the data that we have that comes from real world, and also diversity of data. The data that we can see how the system works under different environment in terms of weather, in terms of geometry of the roads and all of that. And also quality of the data. If the data that we collect, whatever it comes in, how can we work with it no matter how the way that it comes. And also being able to, so we have the data now, but what are the things we can do with this data, and how can we actually test it and see the impact of it, again in a real world scenario. So with all of that, we start, as I mentioned, with the academic government industry partnership to get the idea, to develop the algorithms in the lab, get them out, to test them, and then see the impact, and at that point see what we want to do after with that. Like how do we want it? This is a scalable solution that can be deployed, which I'm going to talk about some of those, or no, this is something that was really good research that we published and we can move on. With all of that in mind, this is where we are today. So we started with those QR codes and the poles, cameras on the poles, but now our technology has been deployed. You can see that this is one of the intersections is about probably close to a mile from Aquarium. If you just go down Broad Street to MLK, and when you hit the MLK, if you look up at any intersections from Highway 27 all the way to Central, you will see a combination of this. This is at MLK in Georgia, and we deployed the first round of technology back in 2018. It went live in 2019, and we are working with the city closely with the federal funds at all the areas shaded that is downtown Chattanooga. We have that technology. But what are the type of technologies that we have? We have cameras. We have different type of cameras, different shapes, different sizes, and also both regular camera and also thermal cameras. We have LiDARs in those to be able to collect data. So that's from the area that we can actually make sense of our environment and understanding what's going on. And in addition to that, you see that we have air quality sensors, we have audio sensors, and then we also have in each of the cabinets, edge computer. We update those as needed. Like started with smaller edge computers. As the need comes up and new smaller computer comes, we have added that. So the one that you see on the graph there, let's see if I want to point this. No. So the darker blue ones are MLK. So that's where you see the darker blue that says 1.5 MLK smart corridor. That's what we have here. And then the rest of them are in plan. Some of them have already been also deployed. And one of the other things that you would see up there is the V2X. And that's one of the areas that has been our main focus, and that's the connectivity. So V2X is vehicle to everything. And basically the goal for us is, and I'm going to show you some of the examples of that, to be able to communicate. Currently, the way vehicles are, even the ones that are autonomous, are working with the sensors that is within the vehicle. So the vehicles, if they are L3 or lower, it relies on the driver to see what the driver sees, and L3 and above also rely on the sensors around the vehicle. What we are saying is like we need to add the connectivity. We need to allow the cars to talk to each other and talk to the infrastructure to be able to understand and see beyond the vehicle driver can see. And that is where the V2X technology is. And you all remember that it used to be SRC, and that technology, that bandwidth doesn't exist anymore, so we are relying more on CB2X, cellular V2X. But some other things that I'm going to be talking about, this is just like a general slide that some of the assets, some of the facilities that we have, how do we really do a lot of our work is we collect all of that. That's a real world. We collect a lot of that. And but one of the things is why I really want to, whatever algorithm we develop, to go out and take a street and test it, that's not the safe way to do it. So we do have a lot of capabilities also to test it on the test track that you see there. That's an area that's about 6 miles campus that we do some testing there. But also what you see on the left side, we have a traffic lab that we do some of the studies there. We have a connection to one of the intersections that we test some of the technologies there. We have a simulator. We do a lot of testing on that, and I'm going to show you that. And we have a team that we test some of the technologies there. But the beauty of this was it's not just hardware. We also a lot of time was actually spent on the data infrastructure part of it, and we call this test bed as a service. Because we understand that, while I come from computer science background, that's my background. I do a lot of data analytics and such. We don't expect everyone to come and use this test have that background. They actually have other expertise that we don't have. So this is the way that we have provided. Everyone can have access to the data. There is a SDK that they can have remote access, and we work with several companies and other universities and Oak Ridge that they have access to our data that they can work with that. And so this is the way that, but currently, if I remember the number correct, over 2 billion data points we collect over a day from just that intersection. So there's a lot of data that we collect. One of the main things about it is we process majority of that in real time, and we don't store any raw data from the video. One of the things for us was when we decided that we needed this bit and we built this bit was community engagement. And that one of the very early on privacy challenges, because this is a regular street. Your business people live there, people have businesses there. So one of our very first promise that we have kept is no video is being stored. What we do is we collect the data from that. We know how, and we call them objects because that's what is in computer vision. That we say how many objects. It was two people waiting to cross. We don't know anything more about them. There were two cars had to wait 30 minutes to cross, which I made it up. 5 minutes on the red light. Those are the information that we collect, and that's about it. So example of like what are we doing? How can this kind of data help us? One of the very like what you see here, this is a campus. What you see on the left, the south side of that street, that's Macaulay. Those of you that know Chattanooga, that's Macaulay Avenue. The south side of Macaulay, that's where our dorms are, and that's where the parking starts. And the north side of it is where the campus is. I pass by that street all the time. The two intersections, signalized intersection are far apart. So many the Chattanooga University Police Department came to us and they have concern about the safety of students and staff that are crossing that. So that's not part of our test, so we do not have a technology. We also have a mobile unit, which you see it on the right side here. We deployed that mobile unit and we collected data over 4 days. You saw that 518 people crossed at mid-block. And you see they cross basically anywhere. And one of the challenges, a major challenge, is the last bullet there. 33 cases that there would have been accident within 2 seconds. Thankfully, there was no accident. But usually what happens? Usually something happens and then we go back and look at it to see what happened. But this was letting us to be proactive about it because this is a learning number to see 33 cases. And these are specifically between a person and a car or a cyclist. So it was not between two cars. We looked at a vulnerable road user and a vehicle. So what we did is we showed this data to Chattanooga Police Department and University Police Department and City of Chattanooga, the Public Works came, and they painted that crosswalk. There's nothing really fancy, literally just painting that crosswalk there. We deployed the technology back for 4 days. You see that, the other one was 518 crossing. This is doesn't want me to show you the results. It's 487 cases of very similar. But one of the things that before this let me go, and majority are crossing now at the crosswalk. There was only 33 cases of not outside of that mid-block crossing. But what I want you to see is zero near misses. And I think that is what. And again, now I'm going to go. Now what I really want to this is what we are trying really to do. To see that how can we proactively make the streets safe. And to do that, we really need to have access to that data, analyze that data, make a view of that, like a holistic view of our environment. And that's what we have been working on. Well, one of the other things that it has become very relevant for us, again, as a university, we usually do not look at economic development impact of our, because that's not in our criteria, that's not in our boxes that we have to do as a faculty or as students. But we have been working very closely with companies, specifically the companies in Tennessee, that like the works that we are doing. You see like examples of the project, for example, they're working with them on risk assessment and post-crash detection. Denso has capabilities with these cameras and connected the roadside units that they have. But this is like really being able to test their devices on the street and helping them develop the algorithm. With LG, we are going to be deploying the first smart crosswalk at LG. I was actually so last week for a visit with them. The smart crosswalks, they're everywhere in Korea, and you see the impact of it. That they detect there is a person on the crosswalk, and they will be able to alert or just have a simple, in some cases that it's dark, it's just a way of having a light on the person that when they know that there's not enough for them to cross the street, or there is a car coming that potentially be an accident. So that would be deployed in Chattanooga. We are actually in the process of that. And the other one is with the startup Aerobill. But moving one of the things I do want to mention is about. I'm going to mention a few projects from now on, but I want to say that our students are the main assets of us, and they're the future of the workforce, and they are the ones behind all of these projects. With that, so let's see some examples. And we have a lot of industry partners that, again, because I use the word we, so I just want to shout out some of our industry partners here. With that, the first project that I'm going to be talking about is this was funded by USDOT a year and a half ago. We are about to finish our first phase of that. And this is about national scalable V2X technology deployment. So the goal of this project is, the example that I showed you about the mid-block. Or the example just generally up to this point. We have done a lot of work. We know where people are, we know where the challenges for the crossing and all of those are. But we don't have a way of communicating. If there is a person on the road, and we know that they are still on the road when the car is coming, we detect it. And we count it as a near miss, but we did not have a way of communicating it to the vehicles around it. And being able to get the drivers alert about it, so they slow down or whatever they need. And that is all about. This is about that part of the connectivity. And our partners are here. In addition to obviously safety, CARDA is our transit agency, and the goal for that is doing transit signal priority for the transit buses. And with 911 and Hamilton County 911 and emergency response, we are doing preemption. I'm going to show you an actual demo that we did with them over the corridor to see how can they get a priority. And also with Hamilton County with the school buses for two things. One is the buses. We have been told by so many different schools and so many counties that one of the challenges is buses get to school late because of the traffic in the morning, and how can they get the priority to get to school on time, and also the safety of kids getting on and off the bus. So those have. But one of the things again like that we do is when we work on this project, because now we're taking the technology out of the lab to this, we need to make sure that we are going to be doing preemption. It needs to work. It needs to work with different technologies, because there are different brands, the ones that exist in the market. We need to make sure that it works with all of them. It can't be just one partner that we're doing with them. But what if the intersection is so interoperability, scalability is really high on our list. So we have built that case in our lab with two different sets of traffic controller boxes, and also different sets of all the things that you see on top are roadside different brands to make sure that it works. With that, one of the things that we did with specifically emergency vehicle preemption was to allow the emergency vehicle to get the preemption to pass. The other thing about it, which is one of the challenges today with autonomous vehicles, I'm sure you have seen those YouTube videos, is autonomous vehicles does not know what to do when emergency vehicles are around, because they don't know if they are behind them or not. That's just not part of the sensing they have. And also, as a human driver, you're driving here, you don't know where the emergency vehicle is going. Is it even relevant to the path you're going? Should you move aside? No, this is another street that you're just here. So those are the things that we want to be able to communicate that. So there are two things. One is preempt the road, but also being able to communicate so the autonomous vehicle or the regular driver know that is on their path or not. So the implementation that what we have done, both part of it is OBU is the onboard unit, is a unit that we put on the bus, on the emergency vehicle to be able to communicate with that. And then also really testing it on the streets to see that how we do the integration. So these are really our team that they have gone to the fire department. Actually multiple fire trucks are now equipped with it, and also making sure that it will be able to do the communication. I have another video, but this is the case that you see that. You can see on top the emergency vehicle is coming, the light is green, red on top of that. But before it gets here, you see that the other side is green, so the cars were going, but before it gets to it, it had already stopped the traffic, and it's giving the right to the emergency vehicle to see. And I want you to see, when you see this video, just pay attention to this part about the phase status and the pedestrian. You see that. And then this is MLK and Market Street. And you see the vehicle, the emergency vehicle, the fire truck will come from the bottom and goes to the top. And you would see that they had the green light already, but it's also making sure that it's locked, so that you will see the vehicle come, and then you see the phase status, lock the other ones on red. And including the pedestrian. Because that's another challenge that when we talk about real world, we actually had that case that so in this case, the light was already green, so they did not have to do anything, but you need to make sure that it extends the red on the other side, because it was actually ending, and it will make sure that all side pedestrians were also red. One of the times that we were doing the test, there was a pedestrian, and this was done in the lab. That's what we could see it. We emulated. We were not on the street doing it. There was a pedestrian there, and there is a minimum time to allow it, and it was 3 seconds, but that was enough for that person to cross. So we need to consider all of those conflicting cases before being able to test it on the street. Another case is cooperative perception. Cooperative perception specifically is important in the case that we see on the right side here for meat blocks. 25% of the accidents that are happening with vulnerable road users happen at intersections. And about 25% of them are happening at block, and especially at night when it's dark. Because in fact, there was an unfortunate fatal accident here in Chattanooga a year ago, or a year and a half ago that happened. That it was exactly that case. Somebody at the very early morning crossing at the crosswalk, but the car did not see it because it was completely dark. So this is the type of thing we are doing two things about. One is If the person is seen broadcasted, so the car would know that there is a pedestrian on the road. The other thing that we're doing is we are working with another industry partner that there is a light there that lit up when it's dark to show that there is a person on the road. So these are I'm going to show you a couple of quick examples. So what you see here, this is MLK and Central. And the one on the right obviously is a camera view. The one on the left is a LiDAR, which we use for all of our research projects. And what you see, or actually it's deployed in the city, so they use it for other purposes too. And what in the middle is what the driver sees. So the person, the little yellow is the person that was walking. And you see that on the middle one, it just all of a sudden the PC, pedestrian in the crosswalk, it comes up so the driver would see it. We'll do it both with the message coming up on the screen and also sound. That it will be again extra alert. But that is also something that we have defined the zones that only when the pedestrian is in that zone to become, because we know that one of the challenges we have is distract the driver and distract the pedestrian. We don't need additional information to distract, but when it's important to receive it, to receive it. So what are the zones that we want that, and what is the threshold of the time that we need to really convey that message, and that's what's happening there. Another example, and this is the case that one of our partners in this project, Audi. So Audi actually has integrated that on their HMI. So like HMI. So you see that person, that's the way they would see it. It's right there in front of them on the windshield, and then there's a sound that comes up, and this is the case that you would see this person coming up, and you would see it also with that. It's a crosswalk. This is a mid. There is that part is like the actual crosswalk we're walking is the other side. So that was the case that we also tested. Okay, so another part. So I'm shifting a little bit from connectivity to digital twin. One of the things that we have been working on is building the digital twin of this. So because we have a lot of data. We collect all of this data on a 24/7 basically, and we have built this twin. We have built the twin more accurate for the corridor, and because we have data that the camera data comes on 30 frames per second. We have bad signal phase timing data that comes at 10. So we have a really accurate data. We can build a real twin of that. And we also understand that that's not the case for always, because some cases we don't have that technology. But even for that, we have looked at average days based on the OD data that we receive from our PA agency. And we have built a twin for that. And we have done several projects so far. I'm going to talk about one here. But we have done a project that the city wanted to see they were planning on a road diet on one of the streets in North Shore. And we modeled. We said that, so that's what is helping, because we can be doing a lot of safety analysis and such on the twin, so that we will be able to see before and after. And many of these you see that. Like basically the way we see the data, we collect that in real time, we label it differently, or one of the ways that we also do it that you see in the bottom right side view is because as a promise for privacy, we do not collect any identifiable personal information. So we do not look at license plate. But we also want to understand if the vehicle passes through multiple intersections, we want to be able to know the same. For example, to know what was the travel time. That would be the only way for us to understand that. So this one, the bottom is actually that. It's a multi-camera, multi-target detection without using any identifiable information. So based on that, we have built a twin. So this is MLK. What you see there, and in the middle is MLK. Is a 2D version, and this is system we were talking earlier. This is a 2D model of MLK, and everything you see there comes from real world. The number of vehicles, what was the status of the light, how many vehicles were in the queue, all of that are in real time, but the colors, type of vehicle, they're random. And that's all, we have done it for all of the part of the corridor. So how did we use this? This was actually in partnership with Georgia Tech, University of Pittsburgh, and Oak Ridge National Lab. How did we use it? I missed that slide, but I can explain it. One of the projects is adaptive traffic control that we do. So we wanted to understand how can we optimize traffic controllers in a way that it reacts to the existing traffic status. Because a lot of traffic controllers are looking at, like either you're using the loop detector, you're using cameras, using LiDAR, or any of those. It's usually look at the current traffic and it decides on that on the next phase. But we did a lot of predictive models because the traffic comes from majority of the traffic comes from upstream or downstream on the main corridors. And based on that, we optimized the traffic controls and we saw that we can improve the travel time by more than 25%. I'm happy to show it to you. I have it on my laptop. For some reason it's not here. But basically we've been able to deploy several cases of that on that twin and testing it. The other way that we are testing that is using the driver simulator. So we actually have the digital twin of our corridor on that, and then we have done many different testing for both autonomous and regular driving with the driver. And we put people like that wearing VR and then think that they are on the road and then see that how would they react, especially the interaction human behavior with the pedestrian and autonomous vehicles. And this is like, we really built the model in a way that as accurate to this. So this is MLK corridor, and this is the model that we have built. So this is almost going to the same. It's a little bit, but even down to the type, the pavement, the signage, all of that, we created it very close 3D model of that. And we ran different, we are doing a lot of different cases. Like you see that we know how those people were standing there. But the age, the height, the clothing, all of those are, again, we make them. Like, it doesn't matter to us, but it does matter to us that how long people waited to cross the street. Because one of the things that when I was talking about the adaptive traffic control, and I don't need to tell you all because you're the experts, but when I'm talking to computer science people for the optimization, we can't just optimize the road for cars. You can't just say that stand there for 5 minutes because I need the cars to pass through because I need to improve my time, the travel time. But like that is why it's important to have all the modes of transportation there. Another way that we are doing is also for driver distraction. So this is a project that we use meta glasses, and that's what you see that that student is wearing. So we're looking to see that where are they looking when they are driving. And then we just provide different distractions to just really, and like multiple times with many different students, we would be testing all of these scenarios to understand when the type of road changes, when the curves and all of that, to understand really being able, and we also do the same thing with the grip and the position of their leg. So the project that, so it was here, that optimizing traffic control. So this is the project that I was just talking about, that how can we use everything for optimizing traffic. So I do have the video to show you here. What you see on the left is the actuator. This is what was happening on a regular day on MLK. That's how the signal is timed. And the other one is the reinforcement learning based algorithm that we have. So what you see on the right side is our algorithm for traffic optimization, traffic control optimization. You see the same number of vehicles, like, because basically it's the same thing. Like the left side had happened one day. It's the data that we got from the testbed. So we have that, but that one you see that it's optimizing for the next one. But look at the one on the right side. It detects the cars coming and it's giving the green time. And you see that how on the left side traffic is building up, but the right side is letting them go. And we have tested this over a long period of time. We tested it on a peak time and a non-peak time as well, over several days, over different times, different seasons, and all of that. And we saw, obviously we had to fine-tune the algorithm multiple times. And one of the other things is because of partnership with Oak Ridge, we were able to actually, it's not working, but we actually ran it in a hardware in the loop. So basically, we were collecting this to one of the vehicles that Oak Ridge lab has, and then they were thinking of that was the code. So we actually measured how much energy was using and how much emission it generated. The last thing that I wanted to talk about is related to autonomous vehicles. So one of the projects that we also have is related to for automation. And connected vehicles. So we have the vehicle in the bottom is a regular vehicle. It does not have, it's not even level 3, probably it's level 1 because it does not have any intelligence. But what it has is we have added the onboard unit. So you see those triangle or cone-shaped antennas on the top. Those are the ones that will provide us the connectivity, so it would allow, so we know where the vehicle is and it knows it can communicate. At this point, all it knows is it can communicate to the traffic controller, so it knows how much is left on the red and those type of information. And the vehicle and the traffic controllers know how many cars are coming through this to understand the message that they send. But the vehicle on the top is actually can be a level 4. We are using it as a level 3 because up to this point, Tennessee has the rule of having level 3 vehicles on the road because the operator needs to be in the vehicle. But it can be fully automated. But we are using it, again, as a level 3. But the application, we're not building a vehicle that is fully automated. That's not this is a vehicle that would retrofit it with our partnership with another company. So we added the sensors we built the algorithms with them. But our goal are 2 things with this. One is adding connectivity. One of the challenges, as I mentioned, for the autonomous vehicles is there are things that, left turns is still a challenge for autonomous vehicles because of perception. The way human minds works is it is complicated to replicate it, to know the left turns. And then and also the example that I mentioned about knowing where the emergency vehicles are or where the cyclists are, knowing ahead of time. We have done many tests that we would have, for example, a bicycle or a scooter that goes faster than a human, all of a sudden showing up in a blind spot. That how would be able to communicate that. So that the connectivity piece is the piece that we are adding and studying that how much that can improve the safety. But also another way that we are currently working on is there a way for us to digitize our environment, to be able to run the vehicle and collect all the data that it can collect. It collects in real time because it needs it for its driving. But that data can also help us for many different things. One is, for example, when the trees or the trees have outgrown, it sees it. I'm going to run this. Hopefully it runs. Yeah, you would see it. It has a very clear view, and this is what only the car has been driving over this corridor only once. And this is the data. It sees the bridge. It sees the signages and everything. So the data that we collect from this, while we need it for mapping because we need the HD map to be able to know plan the path for the vehicle, but we are also using it for knowing where are the parts that, for example, are narrower, because that's one of the challenges for example, transit buses, or where are the places that the trees had outgrown, or the signages are missing. So it can be used for many different applications, and that's one of them. With that, that's the end of my presentation, and happy to answer any questions. Oh, yes, sorry.
Right. Thank you so much for the presentation. That was cool. I have a question on the preemption use case for the V2X technology. And I just want to know if the emergency vehicle communicates at the edge computing level, or it has to be in certain range with the RSU at the signal, communicating with the signal controller. Does it have to be in certain range? And if it does, what at the edge computation level? Are you experiencing issues with the latency? Because safety is very important, and I think these things need to work within a 2-second period, else.
It's a great question. So, and you mentioned latency, and so these are cellular V2X with the latency of less than 100 milliseconds. But we are also looking into network V2X, so that, and we are testing that. We are testing exactly what you're talking about the latency. But in terms of latency, what we are using is 5GAA. I'm not using the right term. It is part of 5GAA. It will come to me. It's certified. So the latency has been tested. But in terms of how we can implement it, in fact, because these are not large scale deployed yet, there are many different ways that it can be deployed. One way is because of the OBUs that is on the vehicles, we know their location very accurately at high frequency rate. So they know where they are, and we detect. We can define the zone. So when the emergency vehicle is in that zone, it knows it's there and it can activate the other one, and that can happen more than 2 intersections away. In fact, the emergency vehicle is a little bit less latency sensitive versus the cooperative perception. Because cooperative perception, you're dealing with, you are at the intersection and a pedestrian or cyclist also all at the intersection. And that is like much faster interaction. Emergency vehicle, we can think about it at least an intersection before, and that's what we want. The goal is really preempted before it gets there. But that's the way we are doing it. We are doing a preemption. But there are, and we have talked with several other state DOTs as well and other that are implementing. One other ways that they're implementing is all red. So they make it red for everyone. So then everybody stops and then the emergency vehicle passes. It hasn't been studied which one is better, but both of them have shown that they would improve both the response time and the safety. But it can be, specifically to your answer, it can be done at least 1 intersection before. And you asked about edge computing, is that? Yes. It does not, because a lot of this process happens at the intersection, at the RSU, which we have an edge computer there. This is really the emergency vehicle. All it needs to do is I'm coming, I'm here, and I'm coming. Because we would know the direction they're going, their speed, and all of that would come from the BSM message they sent through the OBU. Sure. Yes?
I had a question on the equipment. It looks like there are a lot of equipment deployed along the...
Yes.
How often do they get maybe some issues that they have to replace and in terms of maintenance? It looks like there's quite a lot of them.
Right. And one thing I would say is we call the MLK our sandbox because we really deployed a lot. Like the intersection that I didn't show that, we have one intersection that has more than 6 cameras. But that was intentional because we installed the most expensive camera and the cheapest camera because we wanted to learn, and over time, we needed more time to be testing it and understanding the angle, the resolution, all of that to understand that. So based on that, we have reduced. Now what is going to be deployed in other parts is really the minimum required. So we're not having everything there and multiple. So there's a lot of redundancy on what the picture I showed. But your question is absolutely right because there's still, it's a technology, right? It needs maintenance. Thankfully, a lot of it is now software updates. Like our LiDAR, literally yesterday we were on a call, we need to do an update on it. But it's software-based. So a lot of it would be software, but yes, it needs to be maintained. And we are updating them. We are updating not necessarily because they got old or anything. It was because there was a newer one. Again, this is our sandbox because we want to keep making sure that the new technologies are being tested and to see what we can learn from them. Yes?
Why was MLK Boulevard chosen as your sandbox?
When we were deploying it, there was a lot of criteria for us and why ended up at MLK. It has residential. There are not that many streets in Chattanooga that has residential and businesses. And also MLK had just gone through the road diet and had bike lane. Other places in Chattanooga did not have bike lane. And charging stations, public charging stations, because we want to be electrification, automation, and connectivity were our goals when we started it. So those were criteria. And that part of MLK close to Market Street, there's a lot of pedestrian and cyclists because we're not a city that you would see a lot of pedestrian at all intersections. That was, and also being close to campus. So we did not want to be too far from campus because I need students there. But the bike lanes and also being a mix of residential and businesses was the reason. Sure.
This is about the ethical consideration of the data, and
So the data is available to anyone. I mentioned to you as SDK. So there is a data that everyone, like through the SDK, we do have a data user agreement that they need to be filled out because we want to make sure that the data is being used for the reason that it needed to be. So from that perspective. But in terms of the same thing with the emergency, well, we are not collecting data about the emergency vehicle. We are like just, all we are doing is to understand the response time. And that's what actually the fire department has it. We don't have it. We will know what was the response time, what was historically the response time, and what was the response time after this being deployed. So the data that we collect is those digital twins, basically. We have all of that. And that is available to everyone.
I appreciate it.
Thank you.
All right, our last presenter is Jenny Brown. So Jenny Brown is a native of Hilton Head Island, South Carolina, and a graduate of Clemson University Honors College, earning both a Bachelor of Science and Master of Science in Civil Engineering. While at Clemson, she was both a National Science Foundation Graduate Research Fellow and a Federal Highway Dwight D. Eisenhower Transportation Graduate Fellow. Now as an ITS engineer with Kimley Horn, Jenny seeks to lead our industry in developing innovative solutions to complex problems and efforts of improving the efficiency, mobility, and safety for all road users within our transportation networks. Jenny currently sits on the advisory board for the U.S. DOT Center for Connected Multimodal Mobility and is the secretary for the Society of American Military Engineers Huntsville Post. She was recently named a 2024 Huntsville Business Journal's Top 40 Under 40 and a 2025 Top Young Professional by Engineering News Record, Texas and Southeast. She is a licensed PE and PTOE as well as an avid cyclist and Ironman triathlete. Most proudly, Jenny is a wife and mom to 5, including 3-year-old twins. Her and her husband, Aaron, currently reside in Huntsville, Alabama. Above all else, Jenny loves the Lord and daily strives to live her life by Colossians 3:23, which states, whatever you do, work at it with all your heart and working with the Lord and not for men. Please join me in welcoming Jenny Brown.
All right, guys, I'll try to make this fast. All 40 slides of it. Appreciate y'all having me. So I've come up from, I guess, the Alabama representative today for TSITE, Georgia IT. It's been good to see a lot of familiar faces. I was in our Atlanta market for about 10 years and then recently opened our Huntsville, Alabama office. That's that top circle there in Alabama. So we are growing. We now actually have an office in Chattanooga, a little bit over a year now, and as well as Chamblee, Georgia. We just opened a new office there. For those that don't know, Kimley Horn, we're a full-service civil engineering firm. If you name it, we do it. So if you ever have any needs, feel free to call me, but I will dive into the nuts and bolts. So ITS comes to the Rocket City. So today we'll talk a little bit about 321 liftoff. What did that take? Starting our journey from having absolutely no ITS to where we are today. Cleared for landing. Talk a little bit about some of the things we did: drone surveys, FFA permitting. Talk a little bit about all the design criteria we did to get the project up and going. Houston, we have a problem. I'll talk about the district offices, the regional TMC, and all of that were involved in this project. And then forward to the moon, give you a little bit of update on construction and how that is progressing in the area. So for those that do not know, Huntsville is in North Alabama. We're 20 miles south of the Tennessee border. So as you can see on this screen, we have 2 ITS deployment projects going. I-565 from the west to the east. It connects the 65 corridor with Huntsville downtown, and then 65 north to south, down from the Decatur area up to Athens. 565 was the first project that we did. It is fully constructed. 65 is about halfway through construction right now. And then as part of this project, we have the ALDOT Regional TMC, which is there with our little lion friend. It's housed actually in the University of Alabama Huntsville's civil engineering building. They actually will bring in students and hire them to help run their TMC. There's also a district office. The Huntsville district office is right down the street, so we had connections tying back to there. They have an IT server room as well. And then the Tanner district office, which is on the west side, connects the west region to the east region to make the west area with the east area to make our north region. So you have the district offices, regional TMC, and all of that needing connection. There's also a lot of regional coordination as part of this project. Alabama DOT obviously is the main client of ours for the project, helping us do this work, but Redstone Arsenal was also heavily involved. So if you look across the 565 corridor, the Redstone Arsenal, you can kind of see it under the Tiger, but all of that land, it's like 60 square miles. Going along the 565 corridor, we had to coordinate with them on a lot of the technologies that we put out there. For instance, putting a CCTV camera up, we weren't allowed to let it see on the base for security reasons. Huntsville MPO, Decatur MPO, lots of FAA coordination with Huntsville International Airport, Redstone Army Airfield, as well as emergency responders like ALEA, which is the law enforcement agency of the state. So here on the screen was a lot of the project objectives. The main focus for the projects was getting 100% CCTV camera coverage of these corridors. Big time commuter routes from Huntsville to Decatur and Athens, as well as from Birmingham to Nashville, the 65 corridor, making those connections there. So ALDOT really wanted to get the camera coverage. We also installed a few DMS boards, dynamic message signs. And we'll talk a little bit more about that. Road weather information systems in some critical locations, and a few other technologies that you can see there. So one of the cool things that we introduced to ALDOT as part of this project was using drone surveys for the CCTV installation design. So in knowing that their ultimate goal for this project was to get 100% CCTV camera coverage, we brought in one of our drone pilots who's FAA pilot drone license, worked with us to get the FFA permits to get out there and do it. So you can kind of see here, this is at the 565-65 interchange. Just kind of gives a good eyes in the sky of what is that camera actually seeing. It gives you exact coordinates of where you are. I could actually go to an example. So here is, if you look straight, that's Governor's Drive, which is a main corridor to our medical district. Here's I-565 looking east to downtown. Jordan Lane here is another major arterial running north-south, and then 565 west is that way. Oh, there we go. Jordan Lane going north. So one of the benefits about the drone surveys is we can really nail down where we want these cameras to be, the pole locations. They give the exact height of the drone, so we can figure out, hey, what's the lowest pole height we can install out here? How high do we have to go? Where should we install it? Things like that. It'll give the exact northing and eastings. And it's just a really cool way to get a bunch of options. We used to actually go out in bucket trucks. So you'd have to set up the bucket truck, go out in the sky, and you were typically limited to like 40 foot. But now we have these technologies that let us really get all of your options while getting some motion sickness at the same time. So you can see the iconic Huntsville rocket there in the distance. So this one we actually ended up installing right in this grassy area. Gave us phenomenal views of 565, as well as Governor's and then Jordan Lane as well. And this is just a little bit further eastbound. So this is the one that was right before the elevated portion of 565 going into the downtown. You'll be able to see here in a second the horizontal curvature of the roadway, how you lose sight, tree coverage, things like that. So we were able to really hone in on where we wanted, it's going to turn here in a second and show you, where we wanted to show, perfect, So you can see there, like you kind of lose around the bend, you lose your line of sight. So we can fly our drone until we get what we want to see. You can look down, it's going to show you too, look down, what's at the ground there, is it a, feasible option for installation. And so now, like you can see there, you've got much better camera coverage going through the downtown area. And then it'll also look going westbound, and you can still see, you've got great coverage. You can look down, see where am I at. So we ended up installing this one, utilizing existing guardrail right about in this area. So going back to the FFA permitting that I mentioned earlier, across the 565 corridor, we had the Redstone Army Airfield right there, and then actually right where the purple ends is the Huntsville International Airport. Both runways are north-south for all intents and purposes. So the 565 corridor, which is the red line, we were installing 70 to 100, and yes, ALDOT will go to 120 foot for some of their CCTV cameras. So we had to get these FFA permits in. So this is the imaginary surfaces, but essentially each color represents a separate surface area with its own height requirements that have to be evaluated by the FAA. So as part of this, you can go to, FFA has what's called their notice criteria tool, which is what's up at the left. So you can put in all of your data for what you're installing, your pole location, the height, what you're putting on there. And what it'll actually do is tell you yay or nay if you need to apply for our permit. So the things that will typically factor that is what's the height of your structure, what's the proximity to the airport, the location, and even the frequencies emitted from the structure itself. Like, what are you installing on this pole? So a lot of our poles had wireless radios on there. So it's stuff like that that the FAA will take into consideration. So we ended up having 2 poles having to be permitted. Lucky for us, one was with Redstone and one was with Huntsville. This one was the Huntsville, this was right at our minor league stadium interchange. And this is just basically the approved permit. So after the structure's built, you have 5 days to let the FFA know, like, hey, your structure's out there. So DMSs, we installed 565 over the highway message boards. Here were some of the cross sections for those. So typically you'll do survey and cross sections for DMS. For 65, post-COVID, inflation, we ended up going butterfly mount for those DMS boards, so a little bit of a different setup. Over the highway were well over $500,000. The butterflies were about half of that. Soil borings, those start to get into the foundations for your DMSs, but here's one of them that's built out there. That's 565 headed into our downtown area. We actually had a semi-truck last week spilled their load and closed traffic going into downtown. So the DMS was able to route people onto the parkway going south and go around the parkway. So it was really cool. I dropped my kids off and was coming in, and I was like, oh, it's actually doing something helpful instead of just the travel times that it's always had. So that was cool to see. I should have gotten a picture of it, but I didn't. We also installed 5 or 6 RWIS, road weather information systems throughout the corridor. This one here was at the easternly end of 565. So 565 is unique as it goes through downtown. It's about a 2.5 mile elevated section of just bridge as it goes through the downtown area. So this is kind of where it ends and it dips. So they have a really bad incidents history here with crashes from black ice, standing water, things like that. So this was their top location that they absolutely wanted one. So we ended up installing the Luft all-in-one weather smart sensor, which you can see at the top of the pole, and it'll measure everything you see there. And then also as part of that installation, you can see there's the cell modem. So as part of these projects, the initial goal, 565 was 22 miles, 65 was 20. The initial goal was to have full connection, communications connectivity with fiber. But again, money. So We did fiber where it made sense. We brought in cell where it made sense, and then we expanded their existing wireless network where it made sense, and I'll talk a little bit about that. But here, you can see the rocks in the background. Right-of-way was also a big issue in this area, so this pole, and then there's one more, was the end of the line we had as just cell for the RWIZ. Also on that RWIZ pole is the analog infrared camera, and basically what that does is it uses infrared radiation. So it measures the heat coming off of the pavement. So it helps agencies pick up on black ice, snow. So it'll send an alert to the TMC and they know, hey, we got black ice, let's go lay salt. Or we have standing water, let's go fix it or, address it. And, it's also good to just have real data because I don't know if y'all remember this, but, it looks really bad, but in reality, you can see the guys walking in the background. So the data just helps us supplement, what we see on the camera. Like, hey, is it really bad or are we over exaggerating a little bit? So, like I mentioned, we did a lot of fiber routing. We did have a few hub cabinets to tie into the district for future expansion. Just some of the fiber layouts we had. There's the hub actually going to the Huntsville district office. We ended up not putting the hub near the actual TMC because they lease the TMC and their long-term goal is to relocate the TMC to an actual ALDOT facility. So we ended up putting it right near the district office instead and running a 144 trunk to the TMC for now. Again, I-65 had some fiber there as well. This one project, budget was a little less, and we also had the Wheeler Wildlife Refuge going through the project. And ALDOT did not want to open that can of worms, so we ended up doing a lot of wireless communications, and I'll talk about that in a second. But ALDOT in general, because we didn't have a closed loop system, we ended up doing just a folded loop. So I don't know how many are familiar with fiber, but basically let you have some sort of redundancy without actually having a loop of fiber. So we did every third drop, excuse me, was on a different communications group. So you can see the first 4, the next 4, and the next 4, and then the next signal would be there, there, there. So that's kind of how ALDOT requested the redundancy to be done, so we obliged. But again, that's a folded loop. Happy to answer questions after if you have any on that. So the existing wireless network, ALDOT's actually gone pretty big on their wireless lately. So we added, I think, 29 wireless radios as part of this project. So here you can see their existing wireless network. The 565 pole in pink is the I-65, and then so west you had one on Greenbrier at 565, and then two more going north. Actually, during our design, the pole at 565, 120-foot pole started leaning. They were afraid it was going to collapse, so they took it down. So we were able to get our drone survey out there and determine, hey guys, you don't need that 120-foot pole. You can have a 65-foot pole out there. So we were able to have the size of their pole, shore up their foundation, and get that resolved pretty quickly throughout the project. So that was pretty cool to see in action. So as part of the wireless design, what we did was a propagation study. So as part of that, you have what's called a noise analysis, and you have a line of sight analysis. So what you do is you put a scanner, you can see it over there, you take it up into a bucket truck, and you get your data. Your antenna up there will collect the noise and the line of sight data. So the noise data we collected at the 3 frequency ranges below. We'll talk a little bit about that. So when you're dealing with frequencies, you have what's called licensed and unlicensed frequencies. So with licensed frequencies, you basically have exclusive rights to a specific frequency on the band in a particular geographic area, meaning no one else can use it. So you're for sure going to have those rights no matter what. So it's reliable, you know it's yours, but it also comes at a pretty high cost. You've got to pay for that licensing fee. A lot of times you have to pay for the FCC attorney assistance to get those. FCC is the Federal Communications Commission. And the equipment costs are like a lot more expensive. So examples of those is your cell networks, your Verizons, your AT&Ts, commercial radio stations, TV, things like that. You also have your unlicensed frequencies. So with those, the availability, anyone in the public can use it. So you have a specific set of rules, but for the most part, it's like, if it's open, you can have it. There's no licensing fees, equipment's generally cheaper. You do have some regulations, but for the most part, they're pretty, I mean, there's not much to it. It's the EIRP, I think I have it written down. Effective isotropic radiated power, whatever that means. So that's the regulation you have there. But so here, yeah, it's mainly Wi-Fi routers, Bluetooth, consumer radios, and really it's like sophistication versus Wild Wild West. So if anyone knows ALDOT, which route do you think we went? We went the Wild Wild West, right? We're not about to pay for all of the bells and whistles. So with that propagation study, that really helps you figure out what frequencies are available along our corridor so that when we put these radios up, is it going to work? What model brand radio should we go with that's going to operate in those frequencies? So here you have the 900 megahertz, obviously not clean at all. 2.4, you're getting there, and then in the 5 gigahertz, which is what we ultimately recommended going. You had a much better analysis results. My mind went blank. ALDOT uses the Ubiquity radios. That's what they had out in the field. Ubiquity does offer it in this range, so that's what we spec'd out. So that's what they're installing there. We also did, as part of the propagation study, we did a line of sight analysis. So basically, like, can you see it? Direct line of sight. Is there a tree blocking? Is there a building block? Vertical curve, horizontal curve, whatever that might be. So line of sight is part of it. So this was the results of that. Site 16 to 17 basically saw we had no line of sight, and our design was actually, so 17 is actually an existing site at a major highway. So all of our sites were hitting 17, and we had shown in the design to go to 16. So when we got these results back, we're like, oh, we need to figure something out. So 17 was an existing radio that was already making its way to the TMC through the red one above the pink one. It was already going to the marina to the district office. So in essence, everything north of 17 could hit 17 and then get to the marina to the district. So we ended up doing 16, and we took it south to site 14. It had good line of sight there. Site 15 was just a DMS, so it was a short radio. We actually ended up connecting 15 and 16 via fiber so that it would be hardened. But this was just good data. So 16 to 17, you're able to do line of sight analysis. So on the right there is site 17. That's an existing 120-foot pole, so that's set. We did a line of sight analysis at a 70. You can see there's just a crap ton of trees blocking the way. And we even looked at a 120-foot pole at site 16, still not going to work. So if you look at it at site 14, clear as day. So that was really cool to be able to adjust and go that way. ALDOT's TMC, like I said, they pull in a lot of high school students. We've been fortunate enough to hire on board one of them. So one of their college students that was working in the TMC, kind of helping us a little bit on the 565 project. When he graduated, he actually came and worked. He works for us now. So he got to work with me on the design side for the 65 project once it started. So he kind of got to come full circle. But real-time coordination and information dissemination, right? They're pushing out messages to the DMSs. They're reading the data for the RWIZs. They're helping emergency vehicles respond to incidences faster that they see on CCTV cameras, all of that kind of stuff. Algo traffic, anyone in the public can go to algotraffic.com. You can see all of the cameras. Pretty cool live camera feed. So bring it home with construction. So one of the cool things as part of this project was helping ALDOT realize some of the cost savings that you can have with fiber installations. So their specs on the 565 project only allowed for open trenching and boring. You can just see some of the specs there. So boring is a big machine, digs under the ground. I'll show you a video here in a second. Open trenching, you dig a ditch, you have 3-inch deep ditch, usually about 12 inches wide. You lay your conduit and then you refill it. Plowing is a more of a streamlined essence. So directional open trenching is about half the cost of boring, whereas plowing is a quarter of the cost of boring. So half the cost of trenching. So we were able to convince ALDOT that vibratory plowing was a great idea. We brought in clients that we've worked with, other DOTs to kind of speak to, brought in other specs and things like that. So for the 65 project, they actually let us utilize the vibratory plowing, and that's where this detail comes from. On a typical open trenching installation, you can install about 1,000 linear foot a day. When you start getting into the plowing, it's in the scale of 10 to 12,000 linear foot a day. So it really does make a huge difference. And interstate installations are just ideal for it because you can just open it up and go. So this is a plow. Sometimes they'll have a winch truck. Sometimes the plow will have its own motor. But for all intents and purposes, if you look over there on the left, you can see the laying chute. So basically that plow blade is going to make a small cut in the ground, and while it's cutting, it's going to lay both your warning tape and your fiber cable at the same time. And it just drives along. Here is, again, our iconic rocket. So this is 565, so they did open trench on this project. The plowing hadn't been installed yet. But here you can see the construction, the ditch here. It's kind of hard to tell from the proportions of the photo, but it's a 36-inch deep ditch. And ALDOT specs require the fine aggregate to be 3 inches below the conduit and above the conduit of cover for trenching. They don't require that for plowing, so it's another huge cost savings when you start getting into the plowing. And that's what that gray stuff there is. It's that fine aggregate. Here is a directional bore in action. So this was our 65 project. This was a couple weeks ago. We were out in the field with them. So what he is actually doing is he's boring under the interstate. So where he's shooting to is the median, and you can see the guys there. We're providing fiber connection to the existing RWIS that's there. They had a cell modem there, and it hasn't been working for years. So they wanted to get fiber installed from the RWIS to a CCTV cabinet just downstream. You can see he's pulling. Did it stop? It stopped. No, it played through. So those guys on the other side of the street, you can see kind of in the picture on the right, the conduit coming into the ground, and it's going out the ground, and he's pulling it through. And this is the screen that's inside that he's looking at. It gives you like the exact degrees and the depths, and it was pretty cool to watch. But yeah, they pull it out, and then they'll, run your conduits and your fibers through there. Then we did have some bridge installation, so conduit attached to bridge structure. So that's them installing it. A pull box on the bridge, things like that. So lots of unique applications, and that's all I got. Any questions? Yeah. That's a good question. See, his question was how frequently do your cameras have to be placed to get that 100% coverage? So typically a camera so a lot of it depends on client preference on how granular they're willing for their data to be. If you want a really good picture back at your TMC, you won't want to go over like a mile. So that'll dictate a lot. ALDOT was like, we don't care. We don't need to know what color the car is. We don't want to read a license plate. We just need to know if something happens. So if it's a little fuzzy, that's okay. So they were willing to go up to like 2 miles, 2+ miles. And the drone helps too because it's going to give kind of a good representation of, because I didn't show it, but as part of the survey, we'll zoom in and zoom out to see like, all right, if I'm zooming in on the roadway X distance away, what is my picture going to look like? So I mean, we had some instances where we had, curves in the road and we had to, half-mile spacing or whatever it might be. But for the most part, you could get, a mile either direction, typically. Appreciate you.
All right, and with that, that concludes our meeting. I really appreciate everyone for coming out. I appreciate Georgia also for joining us and all the help they provided in putting this meeting together. And everyone have a safe journey back home.